So, what if I told you that right now, inside your body, there's a tiny, microscopic traffic jam happening? A communication breakdown that, for millions and millions of us, is the very first step toward a huge health crisis. Today, we're going to unlock the mystery of insulin resistance.
Just imagine for a second that your cells are like tiny oases, and energy, well, that's the essential delivery they need to keep the lights on. Now, with insulin resistance, the doors are locked shut. The packages of energy start piling up outside, and the whole neighborhood, your entire body, starts to feel the effects. It's a communication failure with some pretty life-altering consequences.
Okay, so what are we really talking about here? Basically, insulin resistance is when your cells just go deaf. They stop listening to the instructions from a super important hormone, insulin. So instead of letting sugar in for fuel, they just don't, and that sugar gets stranded in your bloodstream. Now, this isn't just some small hiccup, this is the central problem, the very foundation of type 2 diabetes.
To really understand what's going wrong, we first have to appreciate the beautiful, incredible precision of how it's all supposed to go right. And that story all starts with insulin and its critical mission. Let's stick with that delivery idea, okay? When you eat something, your blood fills up with glucose. Those are the packages. Your pancreas sees this and sends out insulin. That's our delivery driver. Insulin's whole job is to go knock on the door of each cell and tell them, hey, open up and take this package. When it's all working, it's just this perfectly smooth, efficient energy system.
So how does this cellular delivery service actually pull it off? Let's zoom way in and look at the incredible machinery inside our cells. We're going to follow the entire chain of command. This whole process, and yeah, scientists have a fancy name for it, the IRS/PI3K/ACT pathway, it unfolds in 4 really elegant steps. It starts when the signal arrives, then that message gets relayed inside, a whole conveyor belt system kicks into gear, and finally, the loading doors swing right open. Let's break that down. Okay, step 1, the arrival. The insulin molecule, our dispatch call, finds its one specific receptor on the cell's surface. You can think of this as the receiving dock of a factory, and it's built to perfectly accept this one specific delivery and no other.
But how does that message get from the outside of the cell to the inside? Well, as soon as insulin docks, it triggers a chain reaction. It activates these molecules called IRS proteins. These guys are like the factory's internal dispatch managers. They grab the signal from the dock and get it ready to send deep into the factory floor.
Now this is where the real magic happens. Those dispatch managers, the IRS proteins, they unleash this cascade of signals, first activating PI3K and then ACT. This is the factory's high-tech conveyor belt, a lightning-fast chain reaction that carries the message, get ready for glucose, all the way to the loading bay.
And here it is, the final step. The end of the conveyor belt, ACT, gives the green light to these things called GLUT4 vesicles. They're the loading bay doors. They literally race to the surface of the cell, swing open, and let all that glucose flood inside. The cell gets its fuel, your blood sugar goes down, and the delivery is complete. A perfect system.
But in insulin resistance, this whole beautifully coordinated dance just grinds to a halt. A critical message gets lost, gets ignored, and it creates this dangerous jam in the works.
I mean, the difference is just night and day. In a healthy cell, the signal comes in loud and clear. The door's open, glucose gets inside. Simple. But in a resistant cell, that signal gets blocked right at the start. The doors stay jammed shut, and the glucose? It's just stuck outside, piling up in the blood.
So where exactly is the jam? Well, the whole breakdown happens right near the beginning. The signal that's supposed to get to that dispatch manager, IRS1, gets lost. That one single point of failure is enough to grind the entire PI3K/AK conveyor belt to a stop. The instructions just never arrive.
And the result of that is a cellular traffic jam with system-wide consequences. The GLUT4 doors stay shut. The glucose is locked out of the cells, so it just builds up and up and up in the bloodstream. This is the direct cause of the dangerously high blood sugar that defines type 2 diabetes.
But here's the good news. Understanding the problem is always the first step to fixing it, and scientists have developed a whole toolkit to do just that. They're basically like mechanics, trying to figure out how to get this one crucial conveyor belt running smoothly again.
And there's an absolutely incredible range of strategies they're looking at. Everything from natural compounds like berberine, which can help kickstart that conveyor belt, to traditional drugs we've used for years, like metformin, that help make the cell more sensitive to insulin's signal in the first place. There are even these futuristic methods using tiny DNA nanomaterials. But look closely. They all have the same goal, getting that IRS/PI3K/ACT pathway moving again.
So what's next? Well, understanding this pathway isn't just about treating the problem we have today. It's about unlocking the entire future of metabolic health.
And the scientific consensus on this is crystal clear. Researchers have zeroed in on this one specific pathway. They're basically saying, this is it. This cellular conveyor belt is the key target. It's where the battle against insulin resistance is going to be won or lost.
But the work is far from over. I mean, scientists have a pretty clear to-do list. They still need to figure out exactly how this pathway is different in, say, a muscle cell versus a liver cell. Can they fine-tune treatments to be even more precise? And get this, how do our own gut bacteria play a role in all of this? And of course, the biggest question of all, how do we make sure that what works in the lab actually translates to real solutions for real people?
So when you really think about it, it's pretty humbling to realize that one of our biggest health crises comes down to a single broken conversation happening on a scale we can barely even imagine. It's a powerful reminder that sometimes the biggest breakthroughs come from learning to listen to the quietest whispers. The key to our health might just be hidden in the traffic of our own cells.